We have seen in the previous video how atoms can bond to each other to form small molecules. In this video, we are going to address how we can effectively represent the structure of small molecules. One way to represent molecules is visually using a graph structure. In such a graph structure, the atoms of a small molecule are represented as nodes and the covalent bonds between atoms as edges. Such molecular graphs simplify complex molecular structures into a visual format that can be easily analyzed and understood. Here you can see an example of such a graph structure for the molecule catechol that consists of 6 carbon atoms, 6 hydrogen atoms, and 2 oxygen atoms. If you might not be able to find all carbon and hydrogen atoms, the following rules hopefully help you. Each node in this graph represents an atom that are typically represented by their atom symbol. For example, in the top left corner, you can see atoms represented by O and H, which represent oxygen and hydrogen atoms. The only exception to this rule is that sometimes carbon atoms do not have the atom symbol C. So if you see nodes without a symbol, you know that you have carbon atoms in these places. In our case, we can find 6 such nodes without a label, which are all the carbon atoms that are present in the molecule. Then we have edges that represent the bonds between atoms, where the number of lines indicate the type of bond between two atoms. A single line indicates a single bond, whereas 2 parallel lines, such as in our example, indicate double bonds. And triple bonds would be represented by 3 parallel lines. You still might wonder why we only see 2 instead of 6 hydrogen atoms in the molecular graph. The reason is that hydrogen atoms that are attached to carbon atoms are typically not shown. The reason for that is that we can assume that each carbon atom is bound to enough hydrogen atoms to fill their outer electron shells. Since we know that carbon needs 4 additional electrons to fill its outer electron shell, we know that if we see less than 4 bonds to a carbon atom, we know that it is also bound to hydrogen atoms. For example, for all the carbon atoms in the ring, we see that they have 3 bonds, a single bond and a double bond to carbon atoms, which means that these carbon atoms have 1 additional single bond to a hydrogen atom. The carbon atoms that are bonded to the oxygen atoms have already 4 bonds and thus do not bind to any hydrogen atoms. We can also indicate different spatial arrangements of the atoms in the molecule using molecular graphs, as in this example. Bonds that are represented with solid wedges or solid triangles denote bonds that come out of the plane towards the viewer, and hashed wedges or hashed triangles indicate bonds that go behind the plane. And plane lines, such as all the lines that you see in the upper graph, represent bonds in the plane of the paper or the screen. The exact stereochemistry of a small molecule can be very crucial in many areas, for example, for pharmaceuticals, where the biological activity of drugs can differ significantly between so-called isomers that have the same molecular formula but different spatial arrangements of their atoms. These isomers, in particular enantiomers, which are mirror images of each other, can exhibit dramatically different effects in biological systems. One enantiomer might be therapeutically active, treating a disease effectively, while the other might be inactive or might be even harmful. On the previous slide, we have seen how we can graphically represent small molecules using molecular graphs. However, this is not a very convenient way to encode many different molecules. Instead, we need something that is more compact, storage efficient, and machine readable. This can be some kind of text file encoding the structure of the molecule, which we will look at in a few minutes, or it can be a single string containing all information about the structure of a specific molecule. One of the most commonly used encodings for small molecules are the so-called SMILE strings. SMILES is short for Simplified Molecular Input Line Entry System, and SMILE strings are a way to represent the structure of a chemical compound using a single line of text. Here you see an example of a SMILE string that encodes the sugar molecule glucose. And from the SMILE string, we can get the 2D structure of the glucose molecule. The SMILE string that you see here does not tell you everything about the exact stereochemistry of glucose, opposed to the molecular graph that you have seen for glucose on the previous slide, where we used hashed and solid triangles. But as we will see in a few slides, we can also encode the exact stereochemistry of a small molecule using SMILE strings. We're now going to look at the SMILE specification rules that are a set of rules for representing molecular structures as SMILE strings. First, we're going to look at the most basic rules. Atoms are represented by their symbol, which is typically in square brackets. For example, for iron, we have the representation of the element symbol Fe within square brackets. Hydrogen atoms are usually implied and not explicitly written. This is similar to what we have discussed for the molecular graphs, where we usually do not draw hydrogen atoms that are bound to carbon atoms. Here we typically do the same, but for all atoms and not just carbon atoms. We can omit square brackets around an element symbol if all of the following rules apply. The first rule is that the atom has to be part of these atoms. Otherwise, we always write square brackets around the atom symbol. The next rule is that the atom doesn't have a formal charge, which means that the outer electron shell of the atom has no additional or fewer electrons than it would have in its normal uncharged state. For example, if we have a nitrogen atom with an additional electron in its outer electron shell, we would have a minus sign to indicate the negative charge, and we would have to put square brackets around this. The next rule that has to apply is that we can imply the number of hydrogen atoms. An example for where this is not the case is the following SMILE string. Usually, oxygen binds to 2 hydrogen atoms, forming water, where each hydrogen atom forms a single bond with oxygen. However, if oxygen has an additional electron in its outer electron shell and only binds to 1 hydrogen atom to fill its outer electron shell, we need to indicate this in the SMILE string. The next rule is that the atom also has to be the normal isotope. As we have shortly discussed, isotopes are variants of the same chemical element that differ in the number of neutrons in the nucleus of the atom. If we have an atom present as the most common isotype, we might omit the square brackets. For example, the most common isotype of carbon has 6 neutrons and 6 protons in its nucleus with a mass number of 12, where the mass number is the sum of neutrons and protons. However, if we have a carbon isotope with 7 neutrons, we need to indicate this by using square brackets and writing the mass number in front of it. And the last rule that has to apply so we can omit the square brackets around an atom is that the atom is not a chiral center. The definition of a chiral center is the following. An atom is the chiral center or stereocenter in a molecule if the atom is attached to 4 different groups, for example, to 4 different atoms, and where the mirror image of this molecule is not superimposable. This means we cannot rotate or move the mirror image in such a way that we get the identical molecule. This means that the order in which the groups are attached to this atom matter. In this image, you can see an example for a chiral center, which is the carbon atom in the middle of the molecule. And you can see that 4 different atoms or atom types are attached to this carbon atom. If we take the mirror image, which you can see in this image, you can imagine that you cannot rotate or move the mirror image such that it is identical to the left molecule. This means, depending on in which order the 4 groups are attached to the chiral center, we get a different molecule. We will see in a few minutes how we can specify the order of the attached groups using SMILE strings. But if our atom is not such a chiral center and all the other rules above apply, we can omit the square brackets and simply represent the atom by its element symbol. We're now looking at how we can represent bonds in smile strings. Single bonds are not explicitly represented unless necessary. If necessary, they are represented by a single dash. For example, in ethanol, we have a single bond between the two carbon atoms, and we have a single bond between the carbon and the oxygen atom. But we do not explicitly write those single bonds, but instead the element symbols of the atoms that are bound to each other are simply written next to each other in the smile string. And we can also see that following the rules from the previous slide, we don't explicitly write the hydrogen atoms that can be implied. Double and triple bonds are represented by an equal sign and by a hashtag. We have seen earlier that two oxygen atoms can form a double bond, which we can write as O equal O. And we have seen that, for example, two nitrogen atoms can form a triple bond, which we would write as N hashtag N. If we have a branch in a molecule, we can encode this using parentheses. For example, we can have this smile string with parentheses. When comparing the smile string to a molecular graph, we need to consider that we can start to write down the smile string by starting from any atom in the molecule. Here, the first C in the smile string refers to the carbon atom on the very left in the molecular graph. We see that this carbon atom has a single bond to another carbon atom, and the second carbon atom is connected via a branch and a double bond to a nitrogen atom, and with the other arm of the branch and via a single bond to another carbon atom. Thus, we see that what is inside the parentheses is part of the first branch, and what is coming after the parentheses is part of the second branch. If we need to specify more than two branches that start from a single atom, we use parentheses multiple times, such as in this example. Here, if we start to write down the smile string from the carbon atom in the middle, which has bonds to three different atoms, and we can represent this by using the parentheses twice. And we can have, of course, also branching within a branch, as in this example, where we start to write down the smile string from the second carbon atom on the left in the molecular graph. Here we use the parentheses within the parentheses to indicate that we have a branch within the first branch. Now we want to look at ring and cyclic structures. Rings are indicated by using numbers to represent the connection points. The same number is used for both ends of the ring. For example, in the smile string that you see here, we have 5 carbon atoms connected by single bonds, and then an oxygen atom followed by the digit 1, indicating that this oxygen atom is also connected to the first carbon atom that is followed by a 1. Of course, we can also specify double bonds in such a ring structure as in this example. And if we have multiple rings, we can specify this by using additional digits, as in this example, where the start and the end of the second ring is indicated by the digit 2. If a cyclic structure fulfills certain properties, we categorize it as an aromatic ring, which we denote by writing the elements in lowercase letters. We will not discuss here exactly what these properties are. All we need to know is, for now, that an aromatic ring implies the presence of alternating single and double bonds, and hence we do not need to write the type of bonds in an aromatic ring. An example is benzene, represented by all lowercase letters C. In contrast, in non-aromatic rings, we explicitly write down the type of bonds connecting the atoms of the ring, as we have seen above. A few slides ago, we have seen that if we have an atom that is a chiral center or stereocenter, we have a molecule that is not identical to its mirror image. This means we need to specify the arrangement of the 4 bonds that are attached to the chiral center, and we can do this by using the signs add and double add. We now need to follow these 3 small rules to get the arrangements of the 4 bonds. First, we consider the order in which the bonds appear in the smile string from left to right. Next, we need to imagine we are looking in the direction of the chiral center from the perspective of the first bond that we identified in the step above. And then the other bonds that we already identified are attached anti-clockwise if we use a single @ sign and clockwise if we use a double @ sign. Let us look at an example. Here we have a central carbon atom attached to 4 other atoms. First, we need to find the 4 bonds in the order in which they appear in the SMILES string. We see that first we have a nitrogen atom with a single bond. Then we see that the central carbon atom has a bond to a hydrogen atom. For this carbon atom, we notice 2 things. First, since it's a chiral center, we need to add square brackets around it. And second, here we need to explicitly write the hydrogen atom that is connected or bond to this carbon atom, because otherwise we would not be able to explicitly write down the exact spatial arrangement of this molecule. Following this, we see that we have 2 single bonds to first a chloride atom and then the carbon atom. So the order in which the bounded atoms appear is nitrogen, hydrogen, chloride, and carbon. Now we look from the position of the first bond, which is the bond of the nitrogen atom. In the image below, the nitrogen atom is displayed in blue. And we look from this nitrogen atom towards the central carbon atom, such as in this picture. We now consider the other atoms anti-clockwise around the central carbon atom because we have a single @ sign following the central carbon atom, which means we have a hydrogen atom displayed in white, and then to the left we have a chloride atom displayed in green, and then if we move further anti-clockwise we have a carbon atom displayed in gray. And if we simply replace the single @ sign in the SMILES string by a double @ sign, we consider the atoms clockwise in the order in which they appear, and we see that we get the mirror image of the first molecule. And here you can also see the molecular graphs for both molecules. The last SMILES rule that we are discussing is again concerned with the stereochemistry of a molecule. We can have isomers that change in how the bonds are arranged around the double bonds, as you can see in the example below. Cis and trans are prefixes from Latin, where cis means the side of and trans means the other side of. In terms of molecules, this specifies whether 2 groups are on the same side of a plane, which would be a cis molecule, or on the other side of a plane, which would result in the trans molecule. And whether we have the cis or trans version of a molecule can be specified by forward and backward slash. We always use 2 slashes to specify this. If we have the same slash twice, we have the cis version of the molecule, and if we use the forward and the backward slash, we have the trans version. Here is an example for the arrangement of bonds around a double bond. You can see that if we use the same slash twice, we get the cis molecule, and if we use forward and backward slash, we get the trans molecule. You might have figured out by now that SMILES strings are not unique, meaning that we can have different SMILES strings for the same molecule. For example, depending on with which atom we start to encode. An easy example where we can see this is ethanol. We can start to encode a carbon atom first, or for example, we could also start with an oxygen atom, but both SMILES strings represent the same molecule. If we want to have unique SMILES strings for a molecule, we can use canonical SMILES, which is a set of rules and algorithms that ensure that the same molecule is always represented by the same SMILES string. However, we're not going to discuss those rules. In this course, we will mostly use SMILES strings to describe the molecular structure of small molecules. However, I want to shortly mention 2 alternative methods that you might come across. The first one is INCHI strings. It is similar to SMILES strings in the sense that it can describe the molecular structure of a compound using a single string. The second alternative is the mole file format, which saves in a text file information about the position of all atoms and about their bonds. In this example, you see the mole file of carbon dioxide, a carbon atom connected to two oxygen atoms via double bonds. You can see the coordinates of the three atoms in the upper parts and the bonds in the lower part. You see that the atom 1, the carbon atom, is connected to atom 2, an oxygen atom, via a double bond. And you can see in the next line that the atom 1 is connected to atom 3, the other oxygen atom, also via a double bond.